Currently, my team and I are the only few who know about this project, but now that we've put it through extensive lung simulator testing, we're looking to change that, because we can't afford animal testing on our own. The goal of the project, which began in late March, was to produce a safe, simple, and reliable ICU mechanical ventilator, which could be assembled quickly from readily available components. It is based on tried and true mechanical ventilator designs and is optimized for COVID-19 induced ARDS.
So I'm Landon Ivy, Cornell ECE Ph.D., and I led the project, but I couldn't have done it without the support from Rodrigo Caleo, who helped with the control system and clinician interface, Dr. Guru Khalsa, who guided ventilator design and pulled contacts and resources from the medical field, my advisor, Dr. Amit Lal, who started me on this project and has been very patient throughout the process, Michigan Instruments, who loaned us their dual adult lung simulator and breath simulation module, and Sensorion, who provided us the SFM 3300, which is the best flow sensor on the market. So here's the ventilator in its transport configuration. To save production costs and time, standard off-the-shelf parts were used wherever possible. Every pneumatic fitting is the common 1/8 inch NPT. The 3 black solenoid valves are mass-produced. The 3 white proportional flow control valves, or PFCVs, were built from common steppers and needle valves. 1/2 inch vinyl tubing form the tank and connections. The same metric screw fastener is used throughout. PVC is used to make modular connections. We used Arduino for the control system and a Meanwell uninterrupted power supply. We didn't even have to cut the acrylic for the housing because we used standard 12 by 12 inch sheets. We used only FDA approved biocompatible materials. The barred fittings and solenoid valves are nylon. The PFCV needle valves are polypropylene. The right angle T's are brass that meet NSF 61 safety standards. They're all drinking water safe and RoHS3 and REACH compliant. And finally, the vinyl tubing is food grade. So the clinician software runs on any tablet or computer running Windows, Linux, or Mac OS. A keyboard stand and mouse pad can be attached when needed and removed otherwise. All app functionalities can be interfaced via touch or stylus. So starting off on the pneumatic circuit, we have 2 PFCVs that form the blender for meeting target FiO2, and this valve fills the tank during expiration. This one releases the tank during inspiration. The last PFCV meters inspiratory flow rate, and the last valve removes dead space to atmosphere during expiration so that the non-rebreathing valve's exhaust port can open.
Here's the ventilator configured for ICU operation. I currently have my laptop on here, but you can configure it for desktop as well. You just put the tower down here where the weight is and the monitor where my laptop is. I have the keyboard and the mouse pad installed, but those are removable. This can also be configured for the transport ventilation. So you just remove the stand from the bottom and all of the extra peripherals, and then you can load that into an ambulance or an emergency tent. Looking straight at the ports, we have from the left to the right the patient circuit hose, the pressure line, ETCO2 sensor connection, and the flow rate connection. And then on the back, we have from the left to the right down a no connect port, and then we have the exhaust. Here is the connection for the Arduino to the computer, and here is the AC voltage connection, and then the input oxygen and the input air. So both of those are ICU 50 psi standard air inlets. Next we'll talk about the patient circuit. So this is a novel single limb patient circuit, unlike a dual limb circuit. This is optimized for viral infection combating. So right off the bat, instead of a nasty regular humidifier, we have a viral HMEF. So this does the purpose of humidifying the air from the air compressor, but also trapping any viruses from the patient's expiration line. Everything after that can be considered clean. We have the CO2 sensor first, and then we have the Sensorion SFM 3300 flow rate sensor, and then we have a non-rebreathing valve, and where I have an eraser right now, we could put a external PEEP control valve. Following these lines back, we already talked about those connections. We have produced and tested the AC/VC ventilation mode, which stands for assist control. If I wanted to do that, I would just connect this spontaneous breath simulator here with another non-rebreathing valve to this lung, and then this would become the master lung because of this connection here. It would lift up, and this would be the slave lung. So we would be able to simulate like a spontaneously breathing human being. But today I'm going to show you the more simplified, just VC mode, and we'll do that now. So here's the volume controlled ventilation mode. Starting with the plots, we have flow in liters per minute, pressure in centimeter H2O, volume in milliliters, and then on the bottom we have all of our set targets and current fields displayed, and the alarm max and alarm mins. Starting from the left to the right, we have peak flow, and right now this is set to 127. We can set that all the way down to 60 liters per minute, and this PFC that we built with a stepper would rotate to hit the target peak flow. Here we have PEEP. This we can't control internally, but you can do it with an external PEEP valve, like this one over here. I can increase the inspiration time, but it won't really change until we also increase the tidal volume. The inspiration time can be decreased to more precisely control the tidal volume. I think I'll skip the respiration rate and come back to tidal volume because this is way too slow. A couple of these alarms will sometimes trigger during initial changes to the target fields, but after a couple breaths they'll stabilize and won't trigger again unless something is actually going wrong. There we go. There we go. Anyways, so next is tidal volume. We can set that to be higher. We can go up to 800, which is like crazy high for a 7-foot man. We can achieve that. There it goes. And you can also see here that we're getting up to 800 on the Michigan Instruments lung simulator. And then I'm gonna go back down to a more reasonable about 550. That's what it would take to inflate my lungs. I'm a 5'8" man. And then skipping RR. There's FiO2. We don't have compressed O2 here, unfortunately, so it's just measuring the fraction of oxygen inside the compressed air tank. MV is just calculated based on a couple other parameters. PIP, that's just the peak pressure from the plot up there. Here is P average. We're not calculating that right now. Here's CO2. Unfortunately, the lung simulator lacks the mitochondria necessary to produce any more CO2 than what goes in, so we're just sensing exactly that. Apnea time, that has to do with assist control mode, so right now we just have it set to 0. All of these have alarms that we can set. I'll clear the ones I didn't respond to earlier and give an example of an alarm getting triggered. We can trigger its alarm max by dragging this number below the current reading. Let's choose PIP. And that wraps up this video. I appreciate your time. Thank you.